Peace and welcome. In the last couple of sections, we discussed Hamilton's principle and saw how to derive Lagrange equations of motion directly from that principle. In this video, we're going to look at another example, a simple pendulum. We want to find its equation of motion using Lagrange equations of motion. Let's first draw a quick sketch of it. Here are our xy coordinates. Here's the string, and here's the mass attached to it. Here's the angle the pendulum makes. Call it theta. Let's mark our coordinates real quick. This is the x-axis. This is the y. Notice here. Oh, and the length of the string. Let's call it L. We can set L to equal r, where r is the distance between the mass and the origin of the axis. Notice here that we're dealing with two-dimensional motion in the xy plane, whereas the previous example was only in one direction. Now, we write x and y in terms of theta. So, x is L sine theta. Y is, pay attention here, we have the y pointing in the negative direction. So that's going to be minus L cos theta. Deriving both x and y with respect to time, we get x dot equals L cos theta theta dot. And y dot is equal to minus becomes positive L sine theta theta dot. What do we do now? To write the Lagrangian, we need to find the kinetic and potential energies. T is half m. And since the motion is in both x and y direction, it's x dot squared plus y dot squared. Substitute x dot and y dot. Factor out theta dot squared. We're left with L squared sine theta squared plus L squared cosine theta squared, which is simply L squared. And so T is half m theta dot squared L squared. Now the potential energy, U, is minus m g y. Substitute y. mgl sine theta no, cosine theta. Now that we have the expressions of the kinetic and potential energies, we write the Lagrangian. And it's ready to go into the Lagrange equation. Partial L, partial theta, minus d over dt of partial L partial theta dot equals 0. Start with the first term, partial L partial theta. We derive only the part that contains theta. The term with theta dot is considered a constant when we derive with respect to theta. Now the term partial L partial theta dot. Here the part with theta is constant. I think something is... Oh, I forgot the square on the L. Apologies. Square. Now we're all right. Finally, take the time derivative of partial L partial theta dot. Finally, substitute into Lagrange equation. And here we got the equation of motion for the simple pendulum, using Lagrange equations of motion. To summarize what we did, first we wrote x and y in terms of theta. Then we derived x and y with respect to time. Wrote the expression of the Lagrangian, worked out the kinetic and potential energies, and put them into the Lagrangian. Finally, we used Lagrange equations of motion, and got the equation of motion. That's it. I hope you enjoyed this. See you next time. Peace out.